Okay, quantum physics, right? Animation time. Mm. So the first thing you notice about this is that the light is not coming out in the form of rays, but coming out as a form of particles, right? That is essentially the difference between um, classical physics and quantum physics. Okay, so let's start with introduction. Light was, I will sit down because I'm recording my voice, so I can't stand up and show you more things. But okay, so sorry for the lack of maybe engagement physically, right? Because I'm recording it. Anyway, so light, light in the 1900s, right? In fact, slightly earlier, was thought to be a wave, right? Because they realized that hey, light seems to diffract, light seems to interfere, and what actually can address this phenomenon well is that light is a wave, right? But actually, before this, actually before the 1900s, way earlier, Newton thought that light was a particle. So Newton thought that light was a particle. Then later on, they say no, 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 light is a wave because you see, if light was a particle, it cannot do interference. And then later on, right, they realized that hey, if it was true, if light was actually a wave, it cannot actually explain many of these effects. Right? Today we are starting with the simplest, right, which is the photoelectric effect. Okay, which will be actually the whole topic, the whole chapter of quantum one. Right, so photoelectric effect, let's begin. Right, and for each part, I will give you a guiding question. Those would be the parts that you will have to remember, right? And those are the parts that are actually key. Okay. Why am I doing this? Because every year when I lecture this, well, not many years, but this is, I think, the second year I'm doing this. Right? I learned from my mistakes, right? As you have seen from my feedback. I always send out feedback form, which only 8 of you replied. So I can only learn from 8 of you. So the rest of you, can you go and reply the feedback form for my AC lecture and do so also for my QM lecture? Anyway, so the feedback is that wow, physics, quantum physics is the hardest. So I actually did revamp my notes. I revamped my notes, and a number of you actually did help me improve my notes further. So thank you to all those hidden heroes, some among. Right? So let's start. Photoelectric effect. What is essentially photoelectric effect? Essentially, it is when you have light incident on a metal, electrons are excited. Right, that's essentially it. And you need energy to do so. So light provides a form of energy. Okay? So from the classical point of view, pre-Einstein, you're like, yeah, that makes sense, right? Light energy, electron comes out. Yeah, energy is conserved. But there are some things that are not well documented, which I'll talk in part 3. Okay, so let's look at this in a bit more detail, how they detected it. I introduced to you the electroscope. Electroscope, this is a metal plate, zinc plate, and has a gold leaf here. It's a very thin and light gold leaf. Okay? Gold has this property where you can hammer it and it is super duper thin. Right? So when it's neutral, it lays flat. What the scientists then did was that they introduced negative charges to it. Okay, so when a lot of negative charges is introduced, the gold leaf opens up due to electrostatic repulsion. Next, they put UV light on it. They realized that the leaf came down. And the only way that can happen is that electrons excited. Right? So they say, okay, light causes electrons to exit a metal because the electrons have gained energy from the light and gain enough energy to escape the attraction of the metal. right? So here, what is not realistically true is that you cannot actually see electrons. You can, however, see the decrease in divergence. So of course, they did the test and make sure that it's not other effects happening. Okay, if you were to do this in Singapore, even without the UV light, you will see the leaf decrease. Why? Because air has a lot of moisture, right? Air in Singapore is very damp, very humid. The water molecules will carry away the charges, right? Which is why you don't hold a charge very well. Okay, in overseas you do. Right. So one of the key points to learn at this stage is that these electrons have a special name. They are called photoelectrons. They're electrons that excited after light impinges on them. Okay. Right. Then they also realized there were 4 key observations in this experiment. They realized 4 key observations, which is the moment I shine light onto the zinc plate, the leaf starts to fall. Sorry, so that was instantaneous, right? The moment you shine light on the metal plate, the leaf starts to fall immediately, instantaneously. Okay. Second, if I shine a low frequency light on it, like red color, red has a long wavelength and hence a low frequency, no electrons come out, no matter how long I shine on it. But the moment I increase the frequency to maybe purple, some electrons come out. So there is a threshold frequency for it to work. Okay, so these are the first 2 very, very key and very, very important observations. Number 3, right, the maximum kinetic energy of the electrons that come out, doesn't care about how intense the light is. Okay, so let me give you a demonstration. I can't full screen this because it doesn't allow me to. Right? This is an applet. So if I have an intensity, you can see the electrons. Of course, you can't see the electrons, but this simulation tries to do it for you. You can see that there's a range of kinetic energies of the electron. Right, so the light is coming in, hitting this metal, and electrons are coming out. So these things are seeing floating. So the observation was that number 3, that there's a maximum K of the photoelectrons is independent of the frequency. But independent of the intensity and dependent only on the frequency. So if I were to increase the intensity, I will not change the Ke of the electron. So watch. Did the kinetic energy change? But if I were to increase the frequency, that means I change from violet to UV, the kinetic energy should increase. Very, very obvious. Right? So this was actually what they realized. They're like, that's strange. Right? Because later on I will talk about number 3, which is the contradiction. Right? Okay, go back. Number 4, the rate of emission of photoelectrons is proportional to the intensity of light. Actually, just now I did that. I'm not sure how many of you saw it. So this one you just hard memorize for now, and I give you the word. So for now, I want you to form an interesting story using TIMIRP to memorize these 4 effects. Okay, give you 30 seconds, make an interesting story, a mnemonic to remember this. Ready, go. Okay, memory techniques. You want something that is audacious, something that is bright, something that is very funny, something that relates to you, right? Then you can remember it very well. Even if it's uncouth, it doesn't matter because only you remember it. Huh? Okay, this is mine. Mine is very mild and neutral. The indigo morph is really pretty. So boring. Anyone has very creative ones? I'll share with the next lecture. That is not, that I cannot not record. That I can. So many things that are wrong there. I regret asking these questions. Wow. I need to re-record this lecture already. Oh my god. Okay, but maybe I'll just put it there. Your suggested by a student, not Mr. Ho. Okay, so one of the things here is that you notice that using something very rudimentary like an electroscope, observation 1, 2, and 4 can be observed. How do you show in number 1, right? I show a frequency, when I reach a certain frequency, the leaf goes down, right? Number 2, I shine, it immediately goes down, right? The electroscope. Number 4, how do you show it? When I shine light, I use one UV lamp, the rate goes down slowly. When I use two UV lamps, the rate goes down faster, right? So you could see that just very instinctively using an electroscope. Number 3, how does it show? Oh, well, there was a more advanced experiment that we will show and learn later on. So now let's go into number 3, the failure of classical wave theory. Why is this photoelectric effect? Why is the quantum theory important? It's because classical wave theory states a few things, right? It says, look, if light is a wave, this is what will happen, right? I can shine light on it, and by hanging it there, right? It's a measure of energy. If we use enough radiation of enough intensity, there is enough energy. Electrons will escape. That's what they say. That means if I use red color light, which is of low energy, I can just put it there long enough, right? So the electrons will then escape. Or I can put enough red color lamps. If one red color lamp doesn't allow electron to escape, I'll put 2. If 2 is not enough, I'll put 3. 3 is not enough, I'll put 4. I'll just put enough until there's enough red color light energy impinging on the metal and electron should escape. That is the classical theory. However, that is not true, right? They realized, right, that is not true. When they shine purple light, electrons came out. When they shine light of lower frequency, nothing came up. They say, okay, so if classical light wave is true, let's double it. Let's use 2 torchlights, right? And then they waited, and they waited, and then no electrons came out, right? And if you understand the principle of science, right, we always use this idea of POE. We predict, we observe, then we evaluate. So we predicted that if classical theory was true, electrons will be emitted. If I increase the number of torchlights shining red light. But the observation is that's not true. What's the evaluation? The evaluation must be classical theory is incomplete. Right? The POE idea. Okay? And the second thing about science is that the more interesting things are not the things that concur with what you already know, but the things that goes against what you think will happen. Right? So this is why Lepton quantum theory was born. Right? So observation 1, light is only emitted when it's above a certain threshold frequency, and below that threshold frequency, it doesn't care about the intensity of the light. Okay, I packaged this like this for you because, well, questions come out like this also. Okay, so this is me already helping you to understand and answer your questions better. Number 2, one of the things they realized also was that classical wave theory, if you can let the metal absorb light over time, and it will gain energy over time. So if it's a low intensity, you will take a longer time to gain enough energy. If it's high intensity, a shorter time is needed. However, this was completely revoked. Completely. Why? Because the moment you shine light on it, the moment it hits the metal, electrons are emitted instantly. Instantaneously. Right? So there's no parallel in classical theory. How do you explain that? So again, you're like, oh, okay, this is the second nail in the coffin, right? Let's look at the third one. Third one. They say in classical wave theory, if I shine light of greater intensity, that means instead of one torchlight shining purple light, I shine two, the electrons coming out must have more energy because I give it more energy, the electrons that come out must have more energy. Right? That was a classical theory. Because the wave going in. Right? But that's not true too. What they saw was that when you use two torchlights, the energy of the electrons coming out stayed the same. If you use a fixed frequency, the maximum K stays the same. If you increase the intensity, that means you use two torchlights, you actually increase the number of electrons instead. Right? Which is actually our observation number 4. Okay, so observation 1 to 3 actually contradicts what we observe. Classical theory contradicts the observations. Observation 4 is actually true. However, it's not in the way that I expected it. Right? So you needed a theory from Einstein that will explain away the first 3 observations and will still agree with the number 4 observation. So what was his insight? Okay, what was his insight? Right, so in the future, right, when you become scientists, you do, what is more interesting is not the things that agree with what you already predict, it's what doesn't agree and say, okay, what are the opportunities there for me to develop a new theory? Right, very useful for real life. Right, so quick quiz. What are the 4 observations of the photoelectric effect? What are the 4 observations? You have the mnemonic. What is it? First, it is T is threshold frequency, instantaneous. Next is maximum K is independent of intensity, right? Fourth one, rate of. The last 2 is harder. Okay, so practice. Okay, the last 2 is harder. But which of them contradicts the classical theory? It is the first 3. Very good. Okay, cool. Right, so we need to know this. We need to have this at the back of our heads before we do Einstein's theory, because later on you might forget. Right, you need to constantly ask yourself, does it check this? Does it check this? So these 4 things you have to remember throughout the lectures. Okay, Ken? So I give you 1 more minute to do that. Okay, do it. Go. Okay. So now we can finally start on what Einstein's great idea, right? Actually, at the end of this lecture, right, you will, not this lecture, but this lecture series, these 3 lectures, quantum 1, you will realize that, wow, so easy also can. Einstein, you all know him for his E equals mc squared, right? His relativity. but he won more than one Nobel Prize. You know what is his first Nobel Prize? It's actually on the photoelectric effect. Also, and so if you, once you learn this, it's like, wow, in 3 lectures, that means 3 hours, Mr. Ho can teach you photoelectric effect. It's such a simple idea, and it can win a Nobel Prize. Also, if you go back in time, if you can travel back in time to the 1800s, wow, you will win multiple Nobel Prize. You just come up one theory is one Nobel Prize, another theory is another Nobel Prize. Oh, so cool. I wish I can do that. Okay, so let's talk about Einstein's photoelectric effect. Right, so guiding question, how does Einstein's light differ from light in a classical sense? Right? And to guide our next few chapters, 4.1, 4.2, 4.3, I want to give you an overview. You notice that 4.1 is light and photons. It's the energy that's coming in. 4.2 is about how this energy interacts with the metal. And 4.3 is whatever is left in energy becomes the energy of the photoelectrons. So essentially, we are talking about a conservation of energy equation. And this is the overview that I want you to have. Okay, when we embark on 4.1, 4.2, and 4.3. Okay, can you copy that down somewhere? At the bottom of, or above 4.1, right? That would be a good place to copy down conservation energy. Energy of photons equals energy given the metal equals energy of electrons. Above the line 4.1. Okay. So Einstein's photoelectric effect, right? He explains photoelectric effect using this way. Say that light is no longer a wave. Let's imagine light consists of photons. Actually, he wasn't the first one that thought about it. It was by Planck, Max Planck. So it could have been called the Planck theory, right? But Einstein was the one that put it all together. So Planck suggested that maybe light consists of packets of energy called quanta, which spawned the name quantum physics. Right? So the real person who actually started it all is actually Max Planck, who thought about it as quanta. Right? So quanta, it became photons under Einstein's description. So he said, instead of wave, light consists of photons. That means individual particles. Okay, you no longer think about superposition. You no longer think about amplitude. You no longer think about period and oxidation. No, you think about one ball coming in, hitting another ball coming out. It became that simple, right? Revolutionary. So photons come in, electrons come out. Photons come in, electrons come out. Photons come in, electrons come out. Okay? The amount of time in this animation, man. Right, and you see a few things first. Many photons come in, one electron comes out. Okay, that's the first thing you should see. Right, so Planck constant. So the energy of the photons is given by HF, right, which you'll learn in the next chapter. So here you go. The photon, Einstein defines it as is an indivisible quantum or packet of electromagnetic energy which is emitted, transmitted, and absorbed as a whole. The energy of the photon is given by E equals to HF. Can you copy that down? Right, so the H 6.63 10 to the power minus 34 is given in your in the exam, right? F is the frequency of the light. Interesting trivia, H is the smallest constant that we know of, 10 to the power minus 34. Smallest constant that we know. Right. So example 1, calculate the energy of a photon of orange light of 600 nanometers. So immediately we are talking about the energy of a photon, right? We have already jumped into the quantum range. So E equals to HF. But here I'm being very tricky. I say, look, I give you the wavelength. So you must convert frequency to wavelength. How do you convert that? Light. What's the speed of light? You know that 3.0 10 to the power of 8. So V equals to F lambda. The V is here C, because C is a constant of speed of light. Okay? Once you have that, it's just a substitution of numbers, which is just pure calculator skills. You get the answer 3.32 10 to the power minus 19.
So, if light is not received the wave, right, how do you get a wave?
We will talk about that in quantum 2. Good question by Matthew. If light is a photon, how does it get a wavelength? That is actually in quantum 2. Yeah, you will learn actually about the duality of light. It is both a particle and a wave. Oh. Right. Here I also hijack the storyline. So this is a sub-story and a subplot of the story. I need to introduce to you what is an electron volt. Right? I need to introduce to you the unit of electron volt is the amount of kinetic energy the electron gains when it accelerated through a potential difference of 1 volt. And that's a definition. So already straight up page 42 definition, very important. Right? So 1 electron volt is a unit. Watch, when the words are not italicized, they are a unit. Later on, they will see a italicized E and V, which is the electron charge and the potential difference V. But here it's non-italicized. This electron volt is a unit. So it's a unit of energy. Okay? So in example 1, your 3.32 10 to the power minus 19 actually becomes 2.08 eV. Why do they want to make our life difficult? Wow, one representative energy can already, joules can already. Let's just all use joules all the way. Why use eV? It's because there's no 10 to the power minus 19. It's because it's way easier to represent the energy in eV in some experiments, which we'll see later on. Okay? So later on, when I use joules, when I use eV, you must have the ability to switch between the two. Okay? So the general guidance is eV generally you will not hit 10 to the power minus something. You'll just be like a simple number, 2 point something. Whereas in joules, you will have 10 to the power minus 19 around that. Okay, that's the general guideline. Alright, so this is another slide to show you. If you have an electron that starts off at a negative plate, and you let it accelerate through 1 volt, what will happen? You'll gain KE, you see, faster and faster and faster and faster, and boom. That KE is 1 eV. Okay, that is the physical representation of 1 eV. So once again, 1 eV is 1.6 10 to the power minus 19 joules. Right. I have 20 more minutes. Relationship of energy of light and photons. So now I'm talking purely about the light, but I want to ask you, right? When I talk about light, can I just say I want to change the energy of photon? I cannot, right? Instinctively, we are human size. We cannot control something at that scale. So we must control something else, which is the things that control, which is basically increasing the number of lamps, which is increasing the intensity, or changing the frequency of the light, by changing the color of the light. Right? That's what we humans can see and measure and control very easily. But we need to know what is then the quantum effect happening at the photon level. Okay? So, in 4.1.2, I'm going to talk to you about that. So here, we have a bulb lamp of this wavelength. Right, 450 nanometers or 4.5 10 to the power minus 7, I think. The lamp is rated 150 watts. Right, this is the average power. And 8% of the energy appears as emitted light. How many photons are emitted by the lamp per second? Wow. So here, using what you have learned, you can find the energy of a photon. E equals to HF equals to HC over lambda. Substitute in, key, press, boom, 4.42 10 to the power minus 19. I leave the answer here in joules because later on, the lamp is in watts. Watts is joules per second. So I'm not going to convert this to EV. Although I taught you about EV, I'm not going to convert it. Because I need to know when I want to remain in joules, when I need to remain in EV. So in 1 second, the light energy of the lamp is 150 joules, correct? Because it's 150 watts, in 1 second it'll be 150 joules. And only 8% of it is light, so 0.08 times 150. So you have 12 joules of energy as light. Okay? So if you have total 12 joules of energy and each photon has this energy, what is the number of photons? How do you do it? You take the total divided by the constituents, right? Let's say I say that the total weight of everyone in this room is about 8,000 kg. And I say each person is 60 kg or 50. Let's say an average number. What would the number of people in this room? Easy, right? 8,000 divided by 50, correct? It's the same thing that we are doing here. It just looks like, wow, like so tough, but it's actually not. It's very easy, like divide. And in quantum, you just need to divide, plus, you get the answer. Okay, so there you go. Divide, boom. Right? You get 2.71 10 to the power 19 photons per second. Okay? Can? Which means if I increase the number of lamps from 150 watts to 2 lamps of 150 watts, how many photons are there? It will be double. Yes? Okay, good. Next, relationship between the intensity of light and photons. Now, here is where it gets tricky. Right, the 4.1.2 is still easy, 1.3 is harder. We know that intensity is power over area. We then know that power is energy over time. Right, so the intensity here is the intensity, the macro variable, is what is happening to the light. Right, it's the energy of all photons divided by the time times area. Follow me here? From the first to second line, can? Give me a nod if you can. Yes? Okay, so from how power over area becomes energy of all photons over time times area. Then I rearrange, because energy of all photons is actually the total number of photons plus the energy of a photon. So I split up the numerator. Okay? Then I regroup it. I put n over t as one variable, hf as the energy of the photon, and area as area. So this allows me to then write that intensity is the rate of arrival of photons times hf over area. So here is where your friends said that this looked a bit confusing when they first read it. So can you make this change? Can you cancel out? Right, it should be like that. It should be intensity equals to n over t, where nt is the rate of arrival of photons. This should be the better way to represent it. Unfortunately, the feedback came after I printed the notes, so I need you to do some skills in cancelling it out. Okay? Right. So there's a conclusion then, right? If the intensity, that means the brightness of the lamp, is dependent on the rate of arrival of photons, the energy of the photons, divided by area. Area we tend to neglect because we take it as constant. Right? So what can we conclude? We can conclude this. If we are doubling the intensity, that means the lamp becomes twice as bright but it's the same color. That means a blue lamp. I put 2 blue lamps. The rate of photons arriving is double. Okay? Conclusion 2 is a trickier one, right? Many students fall for this, so put a star. If I keep the intensity the same, that means I have the lamp, one lamp having a certain energy, I double the frequency, I change from some color to blue. Right? I change from some very infrared to blue, from 800 nanometers to 400 nanometers. I double the frequency, half the wavelength, I double the frequency. I actually, right, intensity is constant, if HF is doubled, NOT must be half. This is something that was specifically mentioned in all past lectures, but always forgotten. So I want to say it very, very strictly now. And when I read out the Cambridge Examiner's textbook, he also mentioned the same thing. So how important is it, you also know. So it is half, even must know this, when intensity is constant. Okay. Right. We have finished idea of light. We have 10 more minutes to go. So maybe you can talk about photons and how it interacts with the metal. So we have finished the first part, which is the light energy. Now we can talk about the light and the metal. How does it work? When you remove energy, when you remove electron from a metal, right, you must ask yourself, which electron are you removing? For example, if I want to high five one of you in the front row, I just walk over, right? But even to high five some of you at the back row, well, I've got to climb so deep in, right? To high five you. It's the same thing. When the incoming photons high five with the electrons, if you are further in, you must take more energy to pull out that electron. Right? So that's an essential idea of this. Okay? Can? So the electrons at the surface requires the least amount of energy to be ejected. And here it appears the definition, the work function. Very, very important is the word minimum. The work function of the metal is the minimum energy amount of energy required for an electron to escape from the surface. It's a very, very close to the surface, or right at the very, very edge. It's a minimum. Okay, and this has a symbol phi. It's a fishball with a something situate. Okay, phi, pronounced as phi, spelled as PHI, phi. Okay, and different metals have different work functions. More reactive metals tend to have lower work functions. Here's a list of metals for you to get a sense to it, right? Reactive to stable. So sodium is very, very reactive. The work function is very, very low. What is that mosquito? Oh my god, did they just lay eggs? Okay, sorry. There was a, like this size mosquitoes, yeah. I guess I'm the sweetest of them all in this room. Okay, so naturally, platinum, right, is the most inert, right? You know, for those of you who wear jewelry or spectacles, right, sometimes they'll tell you, oh, this is a platinum frame, and they charge you an arm and a leg for it. There's a reason. It's because platinum is, other than being very rigid and very good, right, it's also very not reactive. If you wear a very reactive metal on your hand, you're going to get blisters on your hand eventually because it's going to interact with your body. You're going to get heavy metal poisoning, right? Never wear a lead bracelet on your hand because you're just going to fall sick and die, right? So you're going to learn all these things. Learn physics, save a life. Right, moving on. So let's talk about how photons interact with metals. Right, we said that. So I started, light is photons coming in. The photon is hitting the metal. And how does it actually interact, or what's the probability of interaction, right? I showed you a picture just now, 3 photons come in, 1 electron come out. Actually, that picture is not correct. Okay, the true answer is this. There's actually a very, very low probability. It's so low that literally I had to draw 1,000,000 photons before 1 electron comes out. And so I had to, for the animation that I showed you just now, where 3 kb, 1 come out, I literally had to draw 1,000,000 of that. I will Ctrl+C, Ctrl+V, don't know how many times. And we got to just press the animation and wait, and then see when electron come out 3 hours later. So that's how improbable it is. Right? So actually a majority of the photons do not eject electrons. And those that don't, I got students ask me this, then when does the energy go out? It's absorbed as heat in the metal itself. Also in a photoelectric experiment, you are wasting a lot of energy. No choice. Right? But for science, it doesn't matter. Right? However, with every every electron that must have come out must have interacted with your photon. I think the print there, my English was a bit jumbled up. Right? Every photoelectron that gets emitted must have interacted with and have been ejected by a photon, not the photon. Okay? By a photon. So please make some changes there. Right, I've revamped the notes, so I apologize for not delivering a perfect set of notes. My apologies. Right, so here's something to test. Every photon produces a photoelectron. True or false? Answer is to be shown later on. Every photoelectron must have interacted with a photon. True or false? Okay, physics comprehension. Did everyone pass? 50% is pass, but hopefully you can get 100%. Okay, right? Every photon produces a photoelectron. False, right? 1,000,000 of them produces 1 thereabouts. Okay, and it's also a probabilistic effect. Right, so let's do example 3. In a photoelectric emission experiment, ultraviolet radiation, that means ultraviolet light, of this wavelength of power per unit area of this intensity was incident on a silver surface. This bracket wasn't there. It was the original question is power per unit area. It's a very archaic way of saying it. Alright, so it's a surface of evacuated tube, so the area 12 m² was emitted. A photocurrent of 4.8 10 to the minus 10 amperes was collected. What was the rate of incident photon? What was the rate of emission of electrons? Calculate the quantum yield. So in this question, wow, many things comes out. In your notes, I gave you what is a quantum yield, right? Because I think not many of you know what it is. So this is the original, this was the original question. So what's the rate of incidence of photons on the silver? Using what we have done in the previous part, we find the power again. Power is intensity over area. Intensity is power over area, so power is intensity times the area. So I multiply them together, I get the power. Once I have the power, I know that is the amount of energy per second. Right? I can then do the next part. The energy of a photon, how much is it? Do the same thing, same as the previous part, I get this answer. So rate of incidence, that means the number of photons per unit time. I take 2.5 to 10 to the minus 3 divided by the energy of a photon, I get this. So I have 10 to the power of 15 photons coming in per second. That is a huge amount. Huge. Right? Can you imagine 10 to the power of 9 people? That's the real. How about 10 to the power of 15? It's like crazy, right? Crazy large. What about now the emission, right? So we measure a photocurrent. What's a photocurrent? A photocurrent is just current. right? So first we want to find the rate of emission of what? Of electrons. Okay, this is not, so you have to copy this down to the side. This is a pre-working that is not in your notes. I'll summarize it for you, because once you have read this once, you can do it. Current is the charge per unit time. Charge is the number of electrons times the charge of an electron. So I can rearrange to find the rate of emission of electrons be current divided by charge. Right? This is not exactly new, because in your topic of current of electricity, you actually done something like this. It's just that it's called the number of electrons per unit time, which is in this case the rate of emission. Okay? The same thing. So once you have this current divided by electron charge, you get 10 to the power of 9 electrons per second. That's a huge amount of electrons. I don't kid you. But that's also the amount of electrons that you need to create a current of 10 to the power minus 10, which is not just is a fraction of a nanoampere. So small. And then what is the U? What's the U? Do you need to copy this more? Okay, what is the U? The U is this. You take the number of electrons, what you produce, over what comes in, the number of photons. What do you get? You get 10 to the power minus 7. If you invert this number, you take 1 divided by this number, you get somewhere around 10 to the power 6. Right? So it literally, right, you need about 1 million photons before an electron comes out. And this is standard across most experiments, right? This is the rule of thumb. What metal, whatever light, right? This is how it is. Right? If you want to really ask why, I suggest you study physics in the university level, right? It's just how the structure of an atom is and how unlikely for the photon to interact with the electron because of how tiny the photon is and how small the electron is. Right. I will stop here for today. So next lesson, we will continue with the energies, which is the key part of the photon-metal interaction. Okay, thank you very much.